Yeah.
Yeah, no problem.
to
This is just
their
the
life.
first one.
Peace.
Very nice. Yes.
Okay.
Peace.
All right. That's fine. That's fine. Okay, so we start live streaming so you could start the video. And once it's full, we'll start the program.
climate change are fast becoming a menace to the world. This is no time to cast blame, but everyone must come together deploying innovative solutions to ensure global temperature rise doesn't exceed 1.5 degrees Celsius by 2030. Reports show that the chances are slim, but with the rapid development of clean tech solutions, the mission to a more sustainable future is possible. At Chemotronix, we are integrating digital solutions to accelerate the development of clean tech solutions across various communities, fast tracking our journey to net zero. We have built a decentralized monitoring, reporting, and verification system to rectify the current issues plaguing the carbon credit market. Our solution, financing and developing clean energy solutions, will be faster, cheaper, and easier, ensuring a smoother pathway to net zero. The digital technologies currently utilized involve the combining power of AI, blockchain, clean energy, and IoT to offset greenhouse gas emissions. Our smart IoT device provides real-time monitoring of GHGs, which will help companies and governments align with their ESG goals. To guarantee authenticity, the data is logged onto a decentralized storage, which will help companies offset GHGs and enable purchasing quality carbon credits from pilot projects developed across the world. Our solution provides a network of collaboration between developing and developed countries, fast-tracking our commitment to tripling renewable energy access across the globe, while drastically reducing emissions to achieve net zero in the shortest possible time. This will help accelerate biogas, hydrogen, solar farms, and clean tech solutions, creating at least 10,000 jobs over the next 5 years, impacting over 1 million individuals through the instrument of effective climate financing, while offsetting and avoiding at least 100,000 tons of GHGs in the next 5 years. Chemotronix is changing the narrative of the carbon market to achieve our climate goals. Together, let's journey to achieve a sustainable future.
everyone. Just to confirm that I'm audible. Hi, Peace. Can you hear me, Joshua? Okay, awesome. Hi everyone, welcome. My name is Bolwatife Nishalaya, and I'm super excited to have you all join us. So we are ready to get started. So if you're joining us again, we do say welcome back. We're super happy to have you join us for the fourth time, second time, third time, right? Because this has been like a great series so far. But if you're joining us for the first time, we say welcome. It is because of you that we are so excited to have this set up so that we can have a conversation about the energy transition era. So yeah, we're super excited to have you join us, and we believe that you're in the best place you could be on a Saturday morning or afternoon, whatever the time might be for you. And we assure you that it's going to be a packed session. So do ensure that you stick to us or you stick with us till the very end. So if you can see a poll on your screen, please fill it so we can know where you're joining us from. Hi, Gail from the USA. It's nice to have you join us again. All right. So moving on. So yes, so today we'll just basically talk a bit about Chemotronix and what we do, especially for those that will be joining us for the first time. So Chemotronix is a clean technology company committed to accelerating Africa's transition to a net zero energy resilient future. So we pioneer solutions that combine clean energy technologies, decentralized energy systems, and inclusive climate strategies, especially for undeserved communities. Our work is grounded in sustainability, innovation, and equity. And one of the ways that we do this is through leading energy transition conversations like this webinar. So, this is our fourth episode in the energy transition series. And from the first time, we talked about understanding the role of carbon markets, and which we had Gail on, right, as a speaker. And then the second was on how digital tools are accelerating a net zero future. And the third was on the future of clean energy, EV, and solar. All of these recordings and slides from the previous webinars can be found on our website. You just need to visit www.chemotronix.org/webinars. Right. Okay. So I can take that again, www.chemotronix.org, then slash webinars. Right. So now today, with the topic being energy storage and deployment pathways, we will be exploring practical deployment strategies for hydrogen solutions, systems, and battery technologies. So we'll be examining where each solution excels and where trade-off exists and how hybrid approaches can unlock system level value across power, industry, and mobility. Today's session will bridge engineering fundamentals, real-world deployment experience, and future market outlooks, offering actionable insights for policymakers, developers, utilities, and clean energy innovators. So, as we go on, if you do have any questions, please feel free to drop them in the box, and we would have like a more dedicated Q&A session at the end. So, yes, I think on to our first session of the day. Yes, so we'll just be going through to the next session, which is the welcome address that will be taken by Peace Bello. All right. So yes, Peace Bello is a co-founder here at Chemotronix Limited and is a distinguished leader and innovator, widely recognized for its contributions to clean energy and environmental sustainability. Graduating as the best student in chemical engineering from Obafemi Awolowo University, Peace's academic excellence has been acknowledged by prestigious organizations such as CHEG and the Varkey Foundation, which named him an environmental changemaker of the Global Student Prize. Throughout his career, Peace has been invited to high level forums at renowned institutions, including the United Nations headquarters, the American Institute of Chemical Engineers, Leadership Gathering, Amazon Web Services reInvent, the MIT Climate and Energy Prize, the UNDP Rome Center Youth for Climate, among others. His work continues to inspire thousands of people globally. Passionate about advancing clean energy technologies, Peace co-founded Chemotronix Limited, a company dedicated to developing the carbon market in Africa. His visionary leadership has earned him the AICHE Poda Award for Rising Chemical Engineers. Peace is committed to achieving a sustainable future and believes in the possibility of a just energy transition by 2030. Hi, Peace. It's so amazing to have you on. And I'll just be handing over to you now.
All right, yeah. Thanks so much, Bolu. Thank you very much. Once again, we are very, very happy to have everyone join us. Uh, Thank you, Gil, for joining once again. Thank you, Bolu, for the introduction. And we are so excited to have Matt with us. Matt is just hanging there and he'll be speaking very soon. But just before Matt comes up, I'll be sharing some things just to give a background to what we are discussing today and why the topic is so important, not just uh, not just in Africa but across the globe, right? So I'll be sharing my screen right now, and just let me know when you can see it. Uh,
Yes, I can see your screen, please.
all right. Yeah, thank you very much. We are happy to have you on this call, and today we'll be talking about energy storage and deployment pathways, particularly hydrogen systems and battery technologies. Right. So quickly, I'll be taking you through the energy transition landscape and why energy storage matters. We look at battery storage, hydrogen energy systems, the challenges we are facing, and some solutions as to what lies ahead in coming years. All right. I'm very sure when solar started 10, 15 years ago, some people felt that, or probably solar was not going to become economically viable for people to utilize at that point. But I mean, data has shown from IEA, International Energy Agency, that solar has outgrown expectation, and we can see how the economics has changed, especially in Africa, over the last 10 years. We've seen how we've had lots of large-scale solar projects across rural communities, and that has changed energy access a great mile over here in Africa, right? And moving beyond these, we know that we are not yet where we ought to be, and that's why we must keep on innovating. And I just saw this interesting chart from IRENA's recently released report last month, right? And it highlights a crucial a crucial discussion which focuses on systemic innovation, and it revolves around four building blocks. We have technology and infrastructure, business models, market design regulation, and system planning and operation. I mean, technology and infrastructure seems to be the foundational block, but as soon as you have these technologies, you must rethink how you're going to, ensure it becomes very, very affordable for the end users, be it corporate or private consumers. And that's why innovation is very crucial. And one of the major highlights of these reports was flexible generation and storage, right? And this is one of the focus or the main focus of today's webinar. And I'm very happy that we are discussing this with an expert, Matt, who would shed more light on this later, right? So the global energy storage landscape, This is a data again from Bloomberg, and we've seen a large a large amount of energy storage in the US, China, right? To see them taking a lion's share, and for countries like countries in Africa, Middle East, they are very minute compared to others. Similarly, we've noticed a major a major a major milestone for China, right? Energy storage has tripled in just 3 years, and is because of the access to critical minerals. And this is something that's really helped energy storage in China. But I mean, when we talk of energy access, it has to be across every nation, not just developed countries. Developing countries too must have access to energy storage. And I'll just thought to highlight why energy storage matters. And one of the crucial points is grid reliability. For instance, here in Africa, we all know how we have intermittent electricity access. And if we really want to have reliable energy supply, energy storage plays a very critical role here. And energy storage is one of the building blocks that helps integrate renewable energy sources, because you could have hybrid systems that makes it much more easier and to have a stable and efficient energy supply. So quickly, battery storage. We've seen a lot of batteries evolution from lithium ion to sodium to sodium batteries. We've seen lithium batteries, a lot of even air innovations in the battery space, right? You've had LiO to lithium oxygen from air batteries. But one of the major things that stand out for me is if we get battery storage right, we're going to have better system operation. We're going to have much more reliable solar wind systems, and even much more robust mini grids, right? So we want to really ensure that we intensify our efforts to getting battery storage right, because battery storage is also a very critical lever for hydrogen storage, right? Hydrogen does not operate in a silo. Hydrogen depends on renewables, especially if it's going to be very clean. And this is where electrolyzers come in, because if you want electrolyzers to function efficiently, you must have the right energy source to power it in the right way. At the moment, we have about 100 million tons of hydrogen produced globally, but most of it is from fossil fuels, right? And we are talking of clean hydrogen in the world, right? So if we really want to have clean hydrogen, we must shift away from fossil fuels to having hydrogen from water, which requires an electrolyzer. And this shows that we have a lot of work to do, because at the moment, if we want to have 10% of renewable hydrogen in the market, you're going to need about 100 gigawatts of electrolyzer capacity. And this speaks a lot to the kind of efforts which we have to deploy in coming years. And hydrogen poses a very uh, crucial building block for industries like steel, shipping, and also ammonia, right? So these are the three industries that seem to benefit a lot from hydrogen in coming years. And again, data also shows that little work is being done in Africa. You have most of the efforts being done in China and Middle East. So this webinar is very good. It's very informative for you. Even in Africa, you're thinking of how we could scale up electrolyzer capacity in Africa, right? I'm very sure you're going to learn a lot in this webinar session today, right? It's not to bore you too much on data. Uh, Storage of hydrogen is very crucial because it contributes about 28% to setting up hydrogen infrastructure, right? So you want to ensure you play very crucial role in hydrogen storage, because it plays a very foundational role in the balance of plant system boundary, as highlighted on this dashboard, right? So we could share this slide later for you to read more. But all I'm trying to point out is that hydrogen storage is very important, and we cannot push it to the backside if it is contributing the largest share in terms of cost infrastructure for hydrogen development. We must really pay attention to it in subsequent months and also in our locations, right? And people have argued that hybrid energy systems still offer the most robust solution, because when you collocate a battery system deployment infrastructure with hydrogen infrastructure, with solar, with wind, you have the best cost savings, and you have a lower electricity bill, you have a lower demand charge, you have a lower demand charge, and you have a higher PVC of consumption. So you can see all these things are intertwined, and these are things that we must harness for a very rapid development across the globe, right? So the challenges we've been facing are majorly about costs, supply chain, storage, and transportation, and these are things we must double down on in coming years. All right. So at the moment, hydrogen is still not as cost effective as you have for direct EVs. And this is like a very, very major challenge of how we could reduce the cost of hydrogen to the barest minimum for consumers across the globe. And it's an ongoing effort. And that's why as Chemotronix, we try to design a project which we really hope we could launch very soon. We want to see how we could collocate solar farm, biogas, and green hydrogen here in Nigeria, in Oyo State, right? So we're really looking at how to accelerate this development, and that's why we need your partnership and support to really pull this up, right? So I'll be sharing more on this on our website, so you could read more about the project to see how you could partner with us, right? So what's the way forward? We've said a lot about the problems, the current situation. Battery recycling must be done in the right way. We also want to have a lot of battery storage projects because this is very crucial for hydrogen generation. And again, policy plays a very crucial role, and research cannot be pushed to the background, right? So we can see how all these things connect together. And I really hope that we really, really pay attention to the experts here to see how we could all leverage solutions in our various communities and various organizations to take hydrogen and battery storage to the next level. Thank you very much. Energy storage is very crucial for the future we want. So let's build a sustainable future together. And I hand over now to Bolu. Thank you very much.
Thank you so much, Peace. That was a very, very insightful welcome address. I'm sure we all learned a lot, especially with the energy storage tripling in China. And now we know why energy storage is really important, especially for us who reside here in Africa. All right. I think we can take another poll, Joshua. Can we do that?
Okay, yeah, so
Okay.
yeah.
All right. So on the screen, you can just select what we think our answer should be. The answer should be right. So kindly vote. We are just waiting for you. Kindly select the answer that you think it should be, and we would go on very shortly.
So I think we should just give like 20 seconds for the rest to answer before we move on. Okay. Okay, can you see the result of the poll? Okay, that's, I think I'll just read it out from here. We have like 74. Okay, the first question is, which energy storage technology do you think will scale fastest by 2035? And we have 75% saying they believe lithium ion will still be the one leading ahead of hydrogen storage, which stands as 25. We have 0 for sodium ion and flow batteries. The second question, what do you see as the biggest barrier to large-scale hydrogen energy storage. We have 38% highlighting high cost of production. There's a tie again for infrastructure limitations, same 38%, and 25% go with safety concerns, right? So the third question, in your view, where are batteries most critical today? We have 25% going for electric vehicles, 63% picking grid balancing and renewable integration, and 13% picking remote slash off-grid systems, right? So yeah, interesting to see various insights. So I think, Bolly, you could continue there.
Okay, thank you so much for participating in that poll. We can go ahead. So I'm really excited for the next session. I will be bringing up Matt, who has a lot of years of experience. Like Peter said, he's really the expert here. And yes, so Matt, just a bit about Matt, right? Matt Moran is the managing member at Moran Innovation LLC and previous managing partner at Isotherm Energy. He has been developing power and propulsion systems for more than 40 years and first of a kind gas, slush, and liquid hydrogen systems since mid 1980s. That is really impressive. Matt was also the sector manager for energy and materials in his final position at NASA, where he worked for 31 years. He's been a co-founder in 7 technology-based startups and provided R&D, engineering, and innovation consulting to several hundred organizations. Matt has 3 patents and more than 50 publications, including his online cryogenic fluid management guide and decarbonizing mobility with liquid hydrogen SAE reports. He has created and taught liquid hydrogen courses, webinars, and workshops to global audiences. Matt also writes about liquid hydrogen on his LH2 era blog. And with that, we are super excited to say welcome, Matt, and we are so happy to be able to learn from you. Over to you, Peace.
Thank you, and I'm happy to be here. Thank you for inviting me to speak today. And Peace, thank you for that fantastic presentation. You are a hard act to follow. That's a lot of great information. I'll do my best, but thank you for framing the conversation. Fantastic. I'll try sharing my screen now with my presentation slides, and hopefully that shows up for everyone. Is that showing up here? Perfect. Okay. My expertise is in hydrogen systems and technologies, but I do work in other areas where I have to integrate these systems together, as Peace kind of alluded to. Most of these systems, I should say many hydrogen systems, particularly in the electrical generation grids or microgrids, usually have, if they have a hydrogen system associated, also have a battery system in it to handle transients and surge capacity and that sort of thing. So I agree 100% with Peace's comments that these systems, when you optimize them from a system level, often have a combination of technologies, and that includes hydrogen batteries in many cases. So let me go to the next slide here. Just a quick check. Everybody got to the next slide? I know sometimes things get frozen on the title page. Everyone can see the hydrogen, what, why, what, where, and how at this point. Perfect. Okay. There's a lot of information here, and again, I was glad to see the previous slides. I pack a lot of things into slides too, and break all the rules that you're supposed to do in presentations. So I'm glad to see that Peace is in the same club with me. But I like to provide this because later when you look at these, hopefully there's enough information and links so that you can click on it and drill deeper if you want. But in terms of the why, so hydrogen has kind of some unique characteristics. It's an energy carrier, but also a feedstock for lots of other things, as well as a fuel, and also could be used for energy storage. So that's rather unique. That's why so many industry sectors and applications are beginning to transition to it. And of course, one of the main drivers is that there's no carbon emissions, no soot or smoke at the point of use when you use the hydrogen. Now you have to look at the whole life cycle. How is the hydrogen made and so forth to make sure that the overall environmental impact is positive. The other piece of it is performance. And we'll talk a little bit about this, but hydrogen has a very high performance on some parameters. Limited or no issues related to material supply chains, some of the other things that bedevil other technologies. System lifetimes measured in decades. Many of these hydrogen systems that I was involved in have been in place and operational for 6 decades or longer. And then the other very unique aspect of hydrogen, it's often missed, is that it produces quite a bit of potable water when it's used. So depending on the application in the region and the needs for the particular system, that is an output that you can use for a variety of things. Now the graphic I have here is adapted from the original graphics was from the Department of Energy, the US Department of Energy, showing all the ways that their vision of how hydrogen it's already actually being used. If you look at the far right-hand side, most of those are already been used for decades. Hydrogen has been in play. Mostly industrial applications, so the public generally isn't aware of a lot of these. But there's also a lot of new and emerging applications. And so this is sort of my contents, sort of in a graphic form of what I'm going to just touch on in several of these areas and give you a feel for where hydrogen is starting to play in these applications. And then also, how does it integrate with other technologies, such as battery technologies, as well as renewables and so forth. So a quick background on hydrogen. A lot of people, or I shouldn't say a lot, some people seem to think hydrogen is a quote, new thing because it's new to some of these different sectors. But the reality is that hydrogen systems have been around for a very long time. Jet engines were initially developed in Germany in the 1930s using hydrogen, gaseous hydrogen, as the fuel. It was easy to ignite and throttleable easily for the engines. In the 1950s, a liquid hydrogen jet engine with afterburner was developed and successfully ground tested by Pratt & Whitney. And then there was a series of flight tests that were done also in the 1950s. That flew liquid hydrogen for the first time using an unmodified jet engine and then liquid hydrogen on one wingtip and helium for pressurization on the other. Then in 1966 was the first rocket that had an upper stage with liquid hydrogen in it. That's the Centaur upper stage. And that rocket on the far right-hand side, but I forget now what the payload was. I believe it was a satellite. And it continued then through the Apollo era. So the top 2 upper stages, the second and third stage of the Saturn rocket that was used for all the Apollo missions, was a liquid hydrogen fueled rocket stages, both of them liquid hydrogen and liquid oxygen. You can see at the top middle there, cutaway of the tanks that were used in the common wall between those 2 propellants. At the bottom left is actually the fuel cell that was used to provide the astronauts in all the Apollo missions all of the electricity, heat, and water that they used during the missions to the moon. And the bottom, bottom middle, a little bit more towards the middle, is the fuel cell that was used on all the shuttle missions. And that provided all the electrical needs for the shuttle orbiter when it was on its missions in low Earth orbit. So there's a lot of history there. On the right-hand side is a look at the shuttle program that was between 1981 and 2011. The cutaway of the large brownish tank there is called the external tank, is shown on the far right. And the lower 2/3 or so of that volume is liquid hydrogen, was what was in that volume. The upper 1/3 or so was the liquid oxygen tank. So those fed the engines on the orbiter themselves that helped launch it into space or into orbit. And that continues in the space industry. On the far left is the Artemis 1 depiction. Artemis 2, of course, is about to launch next month. Will be the second launch of this system. This is a full core liquid hydrogen, liquid oxygen stack. So that's first stage and second stage. There's solid rocket boosters on the side. Those are the smaller white side mounted propulsion systems. And then I just want to point out at the bottom far left there, That is the largest operational liquid hydrogen system in the world. I was on the design team for that. I like to point this out because this represents 60 years of large-scale life cycle use of liquid hydrogen that has really tackled all the enabling technologies required for these systems. What's really driving now into other sectors, and what's important, is bringing down the cost, improving and increasing the supply chain for all the other different sectors where these systems can be put in place. A few more on the far right there. I won't go into great detail, but these are, it isn't just NASA. There's around the world a variety of different rockets that use liquid hydrogen either as their both stages, like the Ariane 5 and now the Ariane 6, as part of the European Space Agency, or India for their rocketry, as well as commercial rockets such as the upper stage of Blue Origin and ULA. What we're seeing now, though, is the growth of hydrogen into other sectors. So in this slide, I'm going to talk about probably the closest adjacent industry sector to aerospace and space exploration, and that's aviation. I'll point out on this slide the only one that is a depiction is the top left there. That's Airbus's concept for the next generation hydrogen fueled aircraft. The rest of these photos are all actual photos of flight tests and other equipment that has already been tested with liquid hydrogen. As an example, the bottom left there is Rolls-Royce jet engine that's been tested with liquid hydrogen, ground tested. The rest of them are all in-flight photographs of various aircraft from various organizations within the last few years who have successfully flown with in this case, all but the Beyond Aero is gaseous hydrogen. The rest, and I'm sorry, the Unither helicopter is gaseous hydrogen. They are going to liquid. The rest of them are all liquid hydrogen aircraft, and there's reasons for that. I'll touch on in one of the further slides here. Of course, aviation isn't the only place. Industrial transport applications, large-scale applications like this, where the weight of other options such as batteries starts to become economically and performance-wise not desirable, is where hydrogen is really beginning to get a lot of traction. And again, these are all photographs of operational systems here that I'm showing, actual photographs. There is one Hitachi Energy one in here, steel making, as I think Peace pointed out in his presentation, and other industrial processes have used hydrogen for a long time. What's really changing now is where is that hydrogen coming from, and of course driving towards more green production of hydrogen or reduced carbon reduction if you're doing carbon capture. Other applications getting a tremendous amount of traction is in maritime, various shipping vessels of all types, as well as import and export trade deals and development that is rapidly increasing right now to take hydrogen produced where there are a great deal of local resources, say solar energy, and then producing the hydrogen, liquefying it, and then transporting it similar to the way liquid natural gas is transported now to locations that don't have those resources but want the hydrogen for their end use cases. So an example of that was a few years ago, a successful demonstration of delivery of liquid hydrogen from Australia to Japan. And now there's a great deal more of those kinds of vessels and trade deals that are happening around the world, particularly in the Middle East, producing liquid hydrogen that will be shipped to other locations that need it. A little bit more about some of the infrastructure and liquefaction. There's a paradigm shift here that I want to point out. In our current oil and gas paradigm, you have separate locations where you have extraction of the fuel, then you have to ship it somewhere to then refine it, and then you've got to distribute it to where it's going to be fueled and so forth. Hydrogen has a different paradigm. It can be produced in a separate location, which is kind of the legacy companies have done for many years, Linde, Air Products, Air Liquide. But you also have the option of producing hydrogen where the point of use is. And some of these systems that are coming out now not only produce the hydrogen in situ or at the location of use, it can also be liquefied at that location. So if you think about how much that opens up, not only opportunities and potential for putting these systems in place, but also eliminates a lot of the cost structure associated with that logistics chain when you have distributed parts of your process. Peace touched on this. This is my kind of one slide snapshot of the kind of looking at it from a different aspect. These are from several years old, but there are a couple of studies that were done. On the left-hand side is wind power, on the right-hand side, solar. And one of the things it demonstrates is that adding additional wind turbines or additional solar panels does not take away the inherent intermittency or variation of the power generation that these renewables produce. So right now, what that means is, in a lot of cases, they have to be curtailed. In other words, that power is not used when the demand isn't sufficient, and you have to build out your system such that you can handle the highest demand load. So that's where energy storage starts to come in. Various estimates are usually around 30% when your grid has 30% or more of these intermittent renewables as part of the generation mix. You start to need to bring in storage to really optimize the system so that you can store that energy and then use it when the demand is there, but now your sun has gone down or your wind has reduced. So that's kind of the crux of where storage comes into play. I will point out, and again, this was in Peace's presentations, wind and solar is the lowest cost of electricity method of bringing on new capacity by far. It's not even a close competition. So as he alluded to, if you go back even 10 years ago, lots of people were saying solar and wind was not economically viable. It was never going to be cheap enough. And of course, they were all wrong. It's not only cheap enough, it is completely the lowest potential way to bring on new power. But this storage, energy storage, is a big piece of it. So when you're looking at energy storage, you have some options. I'll just go from left to right. So this is a chart of capacity, power capacity of your energy storage when the demand goes up. So this is how you can deliver that from storage now to your demand, power demand. And then on the bottom axis is the discharge duration. So which of these energy storage methodologies you use, or what combination of them, is going to be driven by your application and your capacity and discharge duration, as well as other parameters. But this is one way to look at it that I think is interesting. So if you go from left to right, you can see things like supercapacitors or flywheels are quite good at a certain capacity range and for short time periods when you need to discharge that stored power back to your grid or microgrid. Batteries cover a lot of ground, up to like a day or maybe a few days, and up to fairly large capacities, 100 megawatts or more. So they're the right solution for a lot of cases. When you start to get up to much higher capacities, though, in the gigawatt range, and durations going from weeks to, like, let's say, a full season, where you might want to store energy that you created during the summer, let's say in northern latitudes where there's a lot of solar radiation, but then in the winter when it gets cloudy and the days are shorter, you need to have that storage available then to follow your demand. Then you've got to go to other solutions. Pumped hydro storage, of course, has been around for many, many decades. It's the most advanced and one of the cheapest ways, where you pump the water up to let's say a lake, and then you run that water down through a turbine, a water turbine with a generator attached to it, and that provides your electricity demand when you need it. Of course, you need the local topology for that. In other words, you need to have some sort of water reservoir at a higher elevation. That's where your energy comes from. It's basically potential energy, gravity driven or gravity fed. Hydrogen storage is the largest option that, in terms of covering a lot of ground in capacity and discharge, and that's one of the things that's driving a lot of the interest in it on for grids, microgrids, and now data center build out that's happening with AI, as well as other things like reliability. I created this about 10 years ago, and it was for microgrids, and I've since come to realize that any hydrogen system is represented by this system's architecture. Now, if you're in a mobile application, for example, let's say a heavy-duty truck or a ship, a large vessel, you might only be, for your particular interested in the generation and the outputs of your system. But somewhere in your supply chain, the life cycle of that hydrogen has to include all parts of this. So it begins with your inputs. What energy are you using? What water sources are you using? Or are you using biomass or other feedstocks? Because you can actually create hydrogen without water. You can also use geologic hydrogen, which I won't talk a lot about in this presentation, but is now gaining a great deal of momentum because there's more and more discoveries of underground geologic hydrogen that renews itself automatically over some period of time, and it will drive the economics quite a bit if it becomes feasible to get a great deal of hydrogen extracted from the ground, lower than $1 per kilogram by some estimates. Then you have to take that combination of inputs and you need to generate your hydrogen, and there's a variety of methods to generate it, and then store it. And you also have some byproducts. Most of those are commercially viable products to sell, depending on what those feedstocks are. And then after a period of time, and this is the key piece with energy storage, there's some time, elapsed time between when you have produced the hydrogen, or if you're using batteries, when you've charged the batteries, and then when you want to use that and stored energy later. And that's what the last two columns are. So you want to be able to generate then either through a fuel cell, which is a electrochemical reaction, electricity, or by combustion, where you can use kinetic or motive either to drive, like say, a turbine generator, which also produces electricity, or that might be your actual output is say through a jet engine, and that's going to provide your propulsion. The other two parts that I think are sometimes forgotten is that there's a lot of heat recovery possible in these systems for all kinds of purposes: cogeneration, running of refrigeration cycles, all kinds of bottoming cycles, all kinds of different things you can do with that heat energy that you can recover from the system, as well as I mentioned before, the potable water, and it produces quite a bit of potable water. So with that kind of overall architecture and thinking about what a hydrogen system end-to-end looks like, let me just show you a few examples of some of these feedstocks. So as was mentioned earlier, steam methane reforming, which is basically natural gas, has been the way that hydrogen has been produced for many, many decades. Now, if you look at the far left-hand side, there's a lot more attention and a lot more demonstrations being done with carbon capture, utilization, and storage. That's what CCUS stands for. So these are sometimes, I'm not a fan of the hydrogen colors. I'll be honest, because I think they tend to smear over a lot of variables that should be looked at very carefully. But people call that sometimes blue hydrogen. You're basically capturing the carbon in some way, shape, or form, and then of course you've got to do something with that carbon. In the middle are some of the bio-waste methodologies I mentioned. Pyrolysis falls into here, as well as lots of other reactions where you can take things such as agricultural waste or even animal waste, and you can produce hydrogen from it. And then the one on the far right is what more people are familiar with: electrolysis, electrolyzers. But there's also direct solar, and that's a lower level, earlier technology that's still being developed. But there are some methodologies looking at nano-engineered materials where you can do direct solar conversion and generation of hydrogen, and lots of other methods. So the point I wanted to make here is there's lots of ways to make hydrogen, and I didn't even include geologic hydrogen, as I mentioned before. So you've got to keep that in mind as you're looking at these systems and what makes the most sense. These are some of the different ways hydrogen can be stored. I won't go into details here other than to say that which one of these methods you choose depends on your application and your operational concept. So the different ones are going to make sense for different types of applications. Liquid hydrogen, just for example, when you want to put a lot of hydrogen on board something like a large mobile application such as a ship or a train, that's where liquid hydrogen begins to become the best solution for that. But there's other ones like underground storage when you're talking about large grid storage that makes more sense. I'll touch this briefly. Most people, I think, are familiar with this, but sometimes this gets lost a little bit in the discussions too. The two ways that I mentioned that you can use outputs. On the left-hand side, there's a fuel cell reaction. So you've got hydrogen and oxygen that goes in, oxygen generally coming from the air, and if it's from air, then it has nitrogen. Out comes that water we talked about. The nitrogen comes right back out as nitrogen again into the air, and then you get electricity and then heat as your other outputs to that process. This is the most environmentally friendly, let's say, method of utilizing hydrogen. On the right-hand side is combustion processes. Now, some processes can't be electrified with fuel cells, batteries, or anything else, or don't make sense to be electrified. Industrial processes, for one, jet engine propulsion, although there are some hybrid methods that are being looked at. But in a combustion process, you've got the same things on the left-hand side of your equation coming in, and you still have water and nitrogen coming out and your heat of combustion that you use for whatever your purposes are. But you also have NOx, and that is a greenhouse gas. And NOx is produced in any combustion process. It has to do with the high temperatures that disassociate nitrogen and oxygen in air, and when they recombine, they form NOx. The interesting thing about hydrogen is, because of its large flammability range, you can get to extremely lean mixtures, and you can drop that NOx down to very low levels that you can't come even close with any other fuel. So that bottom chart on that kind of implies that if you look at the blue line, you can see how far that's the NOx emissions, how far down that NOx comes if you go to very lean mixtures of hydrogen, which are still feasible in mixtures you wouldn't be able to do with any other fuel. I have a few sets of slides here, and I'm going to confess, Peace, I'm not paying attention to my time, so please tell me when I need to hurry up. But I'll take a little less time on these. I just want to show how does this play together a little bit. We talked about that overall architecture. This is an example of a system built from that architecture. This was, again, about 10 years ago on a coastal or island type application that my company was looking at, where you would provide seawater to produce the hydrogen, store it for later, use the potable water for drinking and agriculture, and then this would be a daytime production, as in this example, and then the next slide is then at night, when you lose your solar energy and your demand is now higher than what you can produce with your renewables, you can take some of that hydrogen stored back out, run it through the fuel cell, and load follow now your demand. And there's other things on this particular software that I developed for this, and I used candidate numbers. These aren't the actual numbers. I didn't want to show any confidential data, but for the customer. So these are just candidate numbers, but it gives you a sense of how you balance that storage. And again, a battery system will do the same thing. It's just a matter of, does the size and the needs of your system make sense with just batteries, or with batteries or hydrogen, or some other combination? A few more quick examples. This is something I think is, again, unique to hydrogen. It's the opportunity, if you look at the bottom far right there, of meeting energy security and food security and mobility capabilities all in one system. And this was an example of a team I put together to go after Department of Energy funding. We did not get it. We were in the competitive range, but we didn't make the final cut. But I still think it shows, so this was going to be in Hawaii, the ability, and it was an agricultural based application. So we were going to provide power to an agricultural area for their various systems, hydrogen offtake for their equipment, tractors and other agricultural equipment, fueling for cars and vehicles that are in Hawaii, more common in Hawaii, as well as potable water for irrigation, all with one system. We did get, however, or I am supporting now over the last couple of years, another hydrogen microgrid system, this one also in Hawaii, a very different application, but this is a system that already has lithium-ion battery storage. And our contract was to add hydrogen storage to increase the storage capacity of the overall microgrid. This microgrid already provides all of the power for this particular part of this base. I think I have one more slide. Yes. And this is a kind of a siting overview of where that hydrogen microgrid and the exclusion zone around it for safety reasons, and where it was going to be, or where it would be sited in this particular example. The PDC is the power distribution center that's part of the current microgrid. And on the right-hand side are some of the publicly shared specifications out of the Clean Technica article back in May 2024. 1 megawatt electrolyzer, 600 kilograms of hydrogen stored. Some of it is compressed hydrogen, but also part of what we want to demonstrate is the ability to on-site liquefy So this is all on site. It's taking water supply on site, doing all of this, including liquefaction. And then we want to demonstrate the ability to provide that liquefied hydrogen to various types of aircraft or vehicles that are on site. It also has 600 kilowatts of PEM fuel cells and some of the other hydrogen safety and operational procedures and so forth. And the techno-economic analysis was part of that. So I'll leave, I guess, cut off with this. This is something I put together to help people remember some of the key aspects of hydrogen. I call it the 2020 vision for the countdown to hydrogen. So I'll let you read through this later if you'd like to. I do include 5 safety tips that are critical for hydrogen systems. The last 2 only apply to liquid hydrogen. It has to do with the temperature and phase change that's very prominent in those systems that you have to be aware of. And then on the left-hand side, I'll just point out, this is sort of the dual challenge, both the opportunity and challenge with hydrogen. It has very high gravimetric density, which means the specific energy per unit mass is 3 times higher than legacy fuels. So this is why mobility applications are of such interest, because you can have that energy on board for much lower weight than you would for any other fuel, and certainly much lighter than you would for a battery. But on the other hand, it has a very low volumetric density, so energy density, which means that you have to have larger tanks in order to accommodate the hydrogen. So this is the trade studies that go on when you're actually designing and developing the systems and then deploying them. And with that, I'll stop here and really looking forward to the Q&A session. I have a QR code here for a site that I maintain where I put out a lot of free tools and briefings and materials for folks that want to dig deeper into this topic. And I'll end there. Thank you very much again for the opportunity to present to this audience.
Wow, wow. Can we just give Matt a round of applause? That was a whole lot. I was just trying to, soak everything in. Right. Let's flood the chat session. Right. Thanks so much, Matt. Thank you. Thank you. Thank you. I know you've said a whole lot and people have a whole lot of questions. I also have my questions, right? So, but before we take our questions, I think we should go on a short break, right? So we're going on a short break so that we all get probably a glass of water. Then in 3 minutes, we'll take questions, right? So I'll just launch a quick poll just before we go on a short break. And yeah, we'll just take this right now. So based on what you've heard, I want to hear your opinion. So Martha said a whole lot. So this is how we're gonna know if you paid attention to all what Martha's been saying for the last 20 to 30 minutes. All right. So all right. I'm seeing interesting answers here. Okay. Yeah, we have 20 more seconds for this poll. All right, so I think not to delay us, I'll be ending the poll now and I'll just share the results we have right now. So the first question was, which technology do you believe will dominate long duration energy storage? Right, and 40% went for hydrogen, 60% went for hybrid systems. And the second question, how soon do you expect hydrogen to become cost competitive with batteries for large scale storage? 60% went for 5 years, 20% went for 5 to 10 years, and 20% went for 10 to 20 years. All right, so yeah, really looking forward to the Q&A. I know we'll be able to dive deeper. Right, so Over to you, Joshua. So in 5 minutes, we'll come for the Q&A. So you could just stand up, stretch for a bit before we take. We already have some questions here. You can keep dropping your questions. All right. So in 5 minutes, we'll start the Q&A session. Thank you for staying around. All right. Okay. So Joshua.
The effects of climate change are fast becoming a menace to the world. This is no time to cast blame, but everyone must come together, deploying innovative solutions to ensure global temperature rise doesn't exceed 1.5 degrees Celsius by 2030. Reports show that the chances are slim, but with the rapid development of clean tech solutions, the mission to a more sustainable future is possible. At Chemotronix, we are integrating digital solutions to accelerate the development of clean tech solutions across various communities, fast-tracking our journey to net zero. We have built a decentralized monitoring, reporting, and verification system to rectify the current issues plaguing the carbon credit market. With our solution, financing and developing clean energy solutions will be faster, cheaper, and easier, ensuring a smoother pathway to net zero. The digital technologies currently utilized involve the combining power of AI, blockchain, clean energy, and IoT to offset greenhouse gas emissions. Our smart IoT device provides real-time monitoring of GHGs, which will help companies and governments align with their ESG goals. To guarantee authenticity, the data is logged onto a decentralized storage, which will help companies offset GHGs and enable purchasing quality carbon credits from pilot projects developed across the our solution provides a network of collaboration between developing and developed countries, fast-tracking our commitment to tripling renewable energy access across the globe, while drastically reducing emissions to achieve net zero in the shortest possible time. This will help accelerate biogas, hydrogen, solar farms, and clean tech solutions, creating at least 10,000 jobs over the next 5 years, impacting over 1 million individuals through the instrument of effective climate financing, while offsetting and avoiding at least 100,000 tons of GHGs in the next 5 years. Chemotronix is changing the narrative of the carbon market to achieve our climate goals. Together, let's journey to achieve a sustainable future.
All right. Thank you, Joshua. So I think we'll just go to the Q&A session now. Right, so that we don't delay any of you. We know it's a weekend, right? So thank you once again, Matt. Thank you so much. Thank you so much. Right, so there were two questions in the chat, which I would love you to attend to. The very first one is, what infrastructure? Okay, let me read it in full. Hydrogen is often discussed as a future global energy commodity. What infrastructure investments will be necessary to enable large-scale international hydrogen trade, especially since now I add it's very expensive to transport it. So this is a question from Domenico Perio. So it's actually from Youth for Climate, UNDP. All right, so.
Yeah, it's a good question. I think it's one of the big parts of hydrogen, transitioning to hydrogen, is putting that infrastructure in place. I think what we're seeing now is a consolidation of the best business cases for doing exactly what was described in that question. In other words, where does it make sense to put the infrastructure first? Where can the economics provide a return on investment for the investors that are doing that? And I think what you're going to see is a lot of industrial and transportation applications taking that first step, because they can control the hydrogen production, the distribution, if it is going to be liquid hydrogen used, the liquefaction and so forth, as opposed to more consumer-facing applications. That's my opinion. I think those are going to come later as the infrastructure builds out. Now, more to the point of exporting, I think that was part of the question too. You can look at the work that Oman has been doing. They're building a gigantic port for export, where they're going to be exporting liquid hydrogen out of. As I mentioned earlier, Australia has already done it. They've shipped liquid hydrogen to Japan. So I think those are activities that we need to watch and see which ones work well and which ones need more work. And then the other piece of it, the geological extraction, which I mentioned a couple of times, I think that's another area to keep an eye on, where the costs are going to be probably much lower. And it's going to be distributed in places where oil and gas isn't necessarily distributed now. So that you're going to see, I think, areas that weren't didn't have high energy resources in terms of oil and gas, but now have resources in not just renewables, but also underground geologic hydrogen that they can potentially use as an import-export type of trade.
Yeah, thanks so much for that. I know the argument has always been about how to make hydrogen cost effective, and the levelized, a lot of papers on LCOEs levelized cost of electricity from hydrogen, right? So, but I think just like you've said, I mean, you've been on a lot of projects, right? So I don't think I should add anything to what you've said. It's very clear. Every location is different, and
Yeah,
whatever works in A might not work for B, right? So you just have to look
absolutely.
at your location and see what works for you.
Right.
And I'm curious. You mentioned that you worked on a project that was the largest in the world, right? So I don't know if you could share more insight into what were the things, probably challenges you faced on the project, and like key learnings you think could benefit people that will be listening to this session after, or
Okay.
things that leaders in the sector could take note of. Yeah.
Okay. Yeah, that tank is 5,000 cubic meter volume internal. It's enormous.
That's 5 million liters for those who don't understand the conversion.
Yeah,
So
sorry. Yeah.
that's 5 million liters.
Yeah, it's quite large, and 80 meters in diameter. I'm sorry, 80 feet in diameter. Which, sorry, I'm trying to do the math in my head. 25 meters or so in diameter. So a very large sphere, the largest that's operational. Now there's much larger ones that are being designed right now. Some for shipping and some for stationary, but they aren't online and operational yet. I'd say as far as challenges, the design was actually based largely on a scaled up version of the one that was built in the 1960s that's still being used and has been continuously used through Apollo shuttle and now in the new Artemis. So the same type of sphere, only 50% larger. Some of the challenges were, well, not so much a challenge, it's change in insulation. So the old one was perlite in the vacuum space between the inner and outer tank. This one is using glass bubbles. I think it was a 3M company product, but it provides better insulation, and it also doesn't settle as much as perlite over periods of time. The part that I was in charge or leading and responsible for was the zero boil off system. So I think that was probably at least for me, one of the more challenging parts. It was developing a heat exchanger that went inside this large sphere that would keep the entire contents cool enough that there would be no boil off whatsoever, no vaporization. And then if there was an abort of a mission where they had to push the warm hydrogen back into the tank because the rocket didn't go off, this system had to be able to cool that hydrogen back down to the storage temperature that was needed. So you can imagine how much energy that takes. So I designed that heat exchanger, designed the interfaces, and also made it agnostic to two off the shelf commercial turbo Brayton cryo refrigeration systems, one by Linde, one by Air Liquide. that could actually provide that cooling capacity with a helium cooling loop. So all of that is now part of that design. The heat exchangers inside that tank, the interfaces are there. I think there's another phase of development where they're going to put the required refrigerations in place. And when that's done, there will be no losses whatsoever from that system of hydrogen, which is another big piece of liquid hydrogen systems. I think it's important is to get to that no loss of commodity once you've made it.
Yeah, thank you very much. Apologies to those who might not be chemical engineers, because I
Yeah,
know
sorry.
sometimes
Little detail.
sometimes it could be very, very technical for them. But right, yeah. So I mean, we're talking of energy, and we know that a lot of engineering modeling goes into ensuring these things are very, very technologically sound and viable for end users to use. Right. So now my question is around the transportation. I think you also mentioned cryogenics here again, right? So there's a lot of probably energy loss in that pipeline. I don't know what you think could be done, especially in regions like Africa where we want to start energy projects. I know you highlighted a chart that shows like a uh, very good, very good milestone for hydrogen in energy storage. But I know energy transportation has been where there has been a lot of energy drop, and again, the infrastructure for deployment is also a very big issue for places like Africa that we have barely to none uh, energy hydrogen infrastructure at the moment. So, what advice would you suggest based on your exposure or experience over there in North America? What are the things you think or the mistakes we should not repeat if we are going to start something in Africa?
Yeah, very good question. So the legacy way to deliver hydrogen over many decades until recently was through liquid hydrogen trucks that could travel up to 1,000 miles or more. I don't know how many. I'm not going to do the kilometer conversion, but maybe those who know.
That's like
Uh,
5,000, I think.
Thank you. Yeah,
That's
something in that range
yeah.
of so you can deliver liquid hydrogen that far by truck. That works fine as long as you, of course, don't need large amounts. You can also do it by pipeline in gaseous form, similar to natural gas. However, if you're doing 100% hydrogen, you have to have materials in your pipelines that are not susceptible to embrittlement. So that would be 300 series stainless steels. Aluminum also isn't. Aluminum alloys, various types, are also fine for that service. But probably stainless steel is going to be the most cost-effective way. Now you can do blends, and there's different organizations and utilities that have looked at blends of hydrogen and natural gas in a pipeline that is just a legacy pipeline. Hawaii's been doing that. Hawaii Power has been and gas has been doing that, I think, for over 10 years and has had no issues with it. And I don't remember how high they go. I think it's around 10% hydrogen blend. So there's a couple of examples of ways that you can do the distribution. I do think if you're delivering it by truck, we need to do better about what we just talked about, not having boil off losses. So when you go to most of these trucks won't have to vent on the transport, but when they start to fill the tank at the other end, a lot of times they'll release some of the gas that gets flashed and changes phase from liquid to vapor. It's better to capture that, reliquefy it so that you don't have any losses. The other part of the conversation, I think, in terms of distribution losses is what I mentioned during my presentation. If you can do everything in one site, you've eliminated the distribution losses, essentially. So if you can produce your hydrogen, compress it if you're going to use it as compressed gas, and then use it on site, now you don't have distribution losses. And I think for many applications, that's going to be the better way to go. Everything from airports where you might have to actually liquefy it for larger airports, but smaller ones compressed would probably be fine. I think for microgrids of various types, you could do the same thing. You could actually make the hydrogen on site. And because that potable water is an output, you can either use it for irrigation or drinking, or you can have a mostly closed loop system where you're feeding that water back into your input, your input to your renewable energies to produce more hydrogen. So you're not really using up net amount of water in a region where water is scarce, let's say. So that's kind of a long answer, sorry, piece to your question, but I'm a systems thinker, so I tend to think about all these different ways to tackle the problem, and I think those are the ones that come to the top of my mind when you talk about distribution losses.
Yeah, yeah, yeah. I mean, thanks so much for that. I think we just have 5 minutes more for this session, all right? So the next one here is about, you highlighted energy, food as mobility, and one more as co-benefits. I think an energy as co-benefits of having hydrogen compared to other infrastructures, right? I know you touched a little bit on that in this previous answer. My follow-up question to that is, what do you think could be integrated more into design of projects, particularly in Africa, where you have like large land mass, and we want to solve issues of mobility. So what drivers do you think have to be in place to ensure these projects are able to get offtake agreements in their local communities?
Mm. Well, certainly having signed offtake customers, so that you have some, from an economic standpoint, business model standpoint, so that you have some guarantee of revenue stream from whatever you're building out. I think the other maybe piece of this, and correct me, piece, if I'm going in the wrong direction with your question, but there's a concept of energy nodes where you can build these hydrogen nodes that not only, let's say, provide storage for a grid or a microgrid, but also provide fueling for vehicles and perhaps other use cases for the hydrogen. And these nodes are put in a place where it's convenient and easy for all the different potential users and customers to get access to it. Airports, a lot of airports, international airports that are looking at hydrogen are looking at this energy node concept, and some of them have already started doing it, where they've got a fueling station outside the airport gate, but close to the airport, and then they also are providing hydrogen for fueling of the aircraft.
Okay, yeah, thank you. So before I ask my last question, I want to confirm no one has another question in the audience, right? Because we're about wrapping this up. Okay, so let me ask my question, the last one I have here. So I mean, you talked about electrolyzers. You have more of alkaline at the moment. I think it's about 64% of current electrolyzer technologies, and we have the PEMs coming next. I know SOECs and others are still in development, right? But how can we drive down electrolyzer cost for hydrogen? And that's the first question. The second one is, what alternatives do you think could make us better in terms of green hydrogen? Do you think geologic could play a huge role in coming years, or is it biomass? What are your thoughts about them?
Great question. I think the electrolyzer cost reductions are already happening. I think there's a lot of competition in that space, as you mentioned, piece, with different chemistries, different designs, different approaches. And I also think it's becoming a more competitive space in general. As far as the other methodologies, I think it goes back to what we were chatting about earlier. It depends on the application. I happen to really like a lot of the pyrolysis, and I know we have Liberty online here, whose company does that as well. But when you do a pyrolysis of biomass type inputs or feedstocks, you can end up with a carbon black type of a byproduct, which is very easy. It's both has uses, but it's also easy to sequester. It isn't like the gas. It's not reactive or so forth. So I like a lot of the things I'm seeing coming out in that area. And then as the question mentioned, geologic hydrogen, I think, is the wild card right now. How low can the cost get with that? How much is available, and how quickly can it be brought online? I think are all questions that are starting to get answered now, but we don't really know the full answer just yet. So yeah, I think, and this is an interesting part of hydrogen. There's a lot a lot of methodologies to produce it, and some of the ones that we didn't even get into that much, like direct solar and so forth. So I think there's going to be continued. And by the way, this is very common for these kind of disruptive technology paradigm shifts, where there's a lot of reduction in cost and improvements in efficiency that happens early on in development that, legacy systems have already gotten, optimized out years and years and decades ago. So I think we're going to see a lot more advancements. And just like you had mentioned earlier in your presentation with solar and wind and even batteries, people's predictions right now are going to be probably embarrassingly wrong in just a few years, because there's a large uncertainty associated with predicting the paradigm shifts of this size once they start to scale.
All right. Thank you. Thanks so much, Mart. Thanks so much for answering our questions. So I know people are gonna have many more questions to ask, but what I'll just advise is you could check out Mart's website, h2sage.com, right? So we'll also be sharing the materials later. Mart has a whole lot of resources on hydrogen, uh, especially liquid hydrogen, right? So I've gone through a lot of them, and I must say I don't think I've found any other material like that on any other place, right? So they are one of a kind. So you want to check out those materials if you are looking at energy storage, particularly hydrogen systems. Do well to check out the website, right? So once again, thank you so much, Matt. We'll ensure these is available for people to rewatch. All right. So thank you so much, and thank you to everyone for joining this session. Right. Thank you for tuning in. And also, I'm about to drop off about 20 minutes ago, right? So we appreciate everyone who stayed to the very end. So right now we're almost wrapping up. I hand over to Andrew to give the announcements and closing. Right.
Hello, everyone. Thank you for joining us. Absolutely here, especially Matt. Your session was extremely useful. Thank you for your time. We really appreciate it. I have a number of announcements here before we call it a day. We would like to inform that we are currently hiring for graphics design and video editing positions. The link to register or to apply bit.ly/m/Chemotronix. It's also on our website. So if you have any interests or know anyone who might be interested, please kindly let them know. Also currently working on, like our CEO mentioned earlier, open for partnerships. So please, if you know anyone or if you're willing to partner with us at Chemotronix, we'd love to have you. Also, please join our newsletter where we bring you updates on what we are working on and energy. Visit www.chemotronix.org for more details. Also, finally, please follow us on all our social media channels, Instagram, LinkedIn, and X at Chemotronix. Thank you once again, everyone, for joining us. We really, really appreciate you. Thank you once again, Matt. Thank you. We hope that we'll be able to get access to all those materials you said you'd share with us. Yes, let's have a beautiful weekend ahead of us. Bye, everyone.
Yeah. So Mart has shared the material with me, so I will ensure everyone gets access to it, right? So thank you once again, everyone. Thank you, Matt. We really appreciate your time. Right.
Thank
So looking forward to continue this conversation sometime later. All right. So thank you. All right. Wishing everyone a wonderful weekend. Enjoy your weekend. Thank you.